Good day everyone. So today we're going to discuss some important properties of vector spaces, that is linear independence and spanning set. Spanning sets and linear independence. For this module, we're going to write a linear combination of the set of vectors in a vector space V. Determine whether a set S of vectors in a vector space V is a spanning set of V. And finally, determine whether a set of vectors in a vector space V is linearly independent. Linear combinations of vectors in a vector space. A vector V in a vector space V is a linear combination of the vectors u1, u2, up to u sub k in V, when V can be written in the form V equal to C1U1 plus C2U2 plus and so on and so forth until C sub k, U sub k, where C sub 1, C sub 2 up to C sub k are scalars. We can imagine it as the image that would be formed when you have a printer. Imagine that you ran out of blue. So if you ran out of the color blue, you imagine what possible colors would you be having. So if you have the vector 1, which is yellow, and vector 2, which is pink, what are the possible linear combinations of these colors? So maybe you can have yellow, you can have a lighter yellow, which means that you're going to have a small magnitude of yellow. You can also have pink, a small amount of red with a portion of yellow. And then you can also have orange. Orange is a linear combination. It is a mixture of yellow and red. So if you're going to mix these two colors, you have a linear combination of these two vectors. So if you have purchased your blue ink, then you can have a linear combination of all the possible colors. You can have a mixture of red, yellow, and blue. Or basically our inks is in CMY, cyan, magenta, and yellow. So if you have the linear combination of this, you can have various images or various colors in pictures. Now, let's write the vector W, which is equal to 1, 1, 1, as a linear combination of the vectors in the set. S equal to 1, 2, 3 for vector 1. So this is for our first vector. For vector 2, 0, 1, 2. For vector 3, negative 1, 0, 1. We want to write 1, 1, 1 as a linear combination of the vectors v1, v2, and v3. So just to think of it, how much of red am I going to use? How much of yellow am I going to use? And how much of blue should I be using? If I'm going to mix all of these three colors, can I get black? So that's the problem here. So that's the question. Can I have the linear combination of blue, yellow, and red to form black? So what we're going to do is to find the right proportion, the right amount of C1, C2, and C3 that would form the third vector. So is 1, 1, 1 equal to C1 times the first vector 1, 2, 3, C2 times 0, 1, 2, and C3 times negative 1, 0, 1. If we're going to distribute C1, so that would be C1 times 1, C1 times 2, C1 times 3. And the same with the other element. C2 times 0, C2 times 1, and C2 times 2. And C3 times negative 1, C3 times 0, C3 times 1. Doing that and expanding, we are going to have C1 plus 0 C2 minus C3. So C1 minus C3. For the third element, 3C1 plus 2C2 plus C3. 3C1 plus 2C2 plus C3. So we can say that we have 1, 1, 1, and then we have 1 is equal to C1 minus C3. While 1 is also equal to 2C1 plus C2. And 1 is also equal to 3C1 plus 2C2 plus C3. Taking note of that, you're going to see that here. So C1 minus C3 is equal to 1. 2C1 plus C2 is equal to 1, and 3C1 plus 2C2 plus C3 equal to 1. We can write this as an augmented form of matrix 1, 0, negative 1, 1, 2, 1, 0, 1, and 3, 2, 1, 1. Now this is the augmented form, augmented matrix. From this, you're going to apply the reduced row echelon form of this matrix, and we're going to find, by Gauss-Jordan elimination, we can get the solution. So the solution for this one would be C1 minus C3 plus 1, C2 plus 2C3 equal to 1, equal to negative 1. So we can say C3 is equal to the parameter t, C1 is equal to 1 plus t, and C2 equal to negative 1 plus 2t. So this system has infinitely many solutions. It's not unique. There are different ways of obtaining that color. Parang ganun yung nangyari. So from this system, it has infinitely many solutions, and each of the form C1 equal to 1 plus t, C2 equal to negative 1 minus 2t, and C3 equal to t. To obtain one possible solution, what you can do is to let t to be any value. So say for example, t is equal to 1. If we let t is equal to 1, so we have 1 plus 1. So C3 is 1. C1 is 1 plus 1, which is 2. And C2 is negative 1 minus 2, which is negative 3. So thus, you can have the vector W, which is 1, 1, 1, equal to 2 times V1 minus 3 times V2 plus V3. The other choices for T would yield different ways to write W as a linear combination of V1, V2, and V3. Spanning sets. What is a spanning set? Let the set S to be defined to be the set of vectors V1, V2 up to V sub k. Be the subset of a vector space V. The set S is a spanning set of V when every vector in V can be written as a linear combination of vectors in S. In such cases, it is said that S spans V. So is the set S complete enough to define all the possible vectors in V? Show that the set S 1, 2, 3, 0, 1, 2, negative 2, 0, 1 spans R cube. We want to determine if these three conditions is enough to span R cube. So imagine all the engineers from the past thinks that CMY, cyan, magenta, and yellow is sufficient to produce all the possible colors. So I think it's really CMYK. So cyan, magenta, yellow, and black is used to generate all the possible pigments. Now, in television, to produce a picture, we use RGB, the red, green, and blue. The linear combination of these lights form images on your screen. Now, what we want to do is to check whether this linear combination of these vectors form a span for R cube. So let U be equal to the set of vectors U1, U2, and U3 in R cube. We're going to find the scalars C1, C2, and C3 such that all the vectors U can be represented by a linear combination of these vectors. So again, we have C1 times V1, C2 times V2, and C3 times V3. So that would be 1 C1 plus 0 C2 minus 2 C3. And that would be this first element. For the second one, it would be 2 C1 plus C2 plus 0 C3. For the third element, 3 C1 plus 2 C2 plus C3. So the linear combination of this should be any vectors of the form u1, u2, and u3. So from this, we have c1 minus 2c3 is equal to u1, 2c1 plus c2 is equal to u2, and 3c1 plus 2c2 plus c3 is equal to u3. The coefficient matrix of this system has a non-zero element. The system has a unique solution. So, in any vector in R cube can be written as a linear combination of the vectors in S, and you can conclude that the set S spans R cube. So maybe you want to check for the coefficient matrix. So that's 1, 2, 3, 0, 1, 2, and negative 2, 0, 3. We can get the determinant of that matrix A, the coefficient matrix. So that would be 1 times 1 times 3 plus 0 plus negative 2 times 2 times 2 minus upward diagonal negative 6 plus 0 plus 0. So if we're going to simplify this, this would be 3 minus 8, negative 5 plus 6 equal to 1. So this is not equal to 0, meaning it is consistent. If it is a consistent, then there is a solution. If there is a solution, then S spans R cube. Definition of the span of a set. If S is composed of the vectors v1, v2, v3 up to v sub k, so we say that S is the set of vectors from v1 up to vk, then the span of S is the set of all linear combination of the vectors in S. That is, span S is c1 v1 plus c2 v2 plus and so on and so forth until ck vk, where c1, c2, and ck are real numbers. The span of S is denoted by span S, or span of the set that contains the vectors in S, where span S is equal to V. It is said that V is spanned by the vectors v1, v2 up to vk, or simply S spans V. For theorem 4.7, span S is a subspace of V. If S is equal to v1, v2 up to vk, is a set of vectors in the vector space V, then span S is a subspace of V. Moreover, span S is the smallest subspace of V that contains S, in the sense that every other subspace of V that contains S must contain span S.